In today's lab, we're going to look at Faraday's law and generators. Faraday's law is a law that gives us a relationship between magnetic field, current, and voltage. Let's start with a short little video clip that pretty much shows exactly what we would be doing in the lab today if we were doing this lab.
Of course, the reason we need to know about electromagnetism is because it is used to generate current. For example, when I dip this magnet into this coil, it generates a few microamps, which can be seen on this microammeter here. Or, if I drop this magnet into this copper tube, it will fall slowly because it generates current on its way down. Now, you can actually see the falling magnet if you add this magnetic field viewing film. Let's imagine that it's the north end of the magnet that's going in first, or in this case, that it's the north end of this magnet that's going into the solenoid coil. What direction is the current going to flow? Well, as it goes in, a current will be generated that points in the opposite direction of the magnet's plunge. That is, as it goes in, it is repelled by the electromagnet. If you use your right hand, it is very easy to predict. Well, that's it. Electricity and magnetism are connected phenomena, but their fields are directed at right angles to each other. So we use the convention of the right hand to predict the relative angles of the fields.
This guy's doing the same lab that we would be doing. He's using an air core solenoid, a magnet, and a galvanometer. A galvanometer is a little device that measures small amounts of current. It's really just kind of it's a different name for an ammeter. This one happens to be really, really sensitive though. So he's actually measuring in microamps, which, if you recall, micro means 10 to the minus 6. So he was using this little device, or this little setup, to actually make some electricity. And it's exactly the same principle that we use to make electricity with generators. So this is actually a steam turbine and generator. I should have found one with the picture flipped around the other way, because this stuff is all the steam that's going into the generator, and the generator is this big red thing way over here. All right, these things are pretty big. If a guy was standing here, they'd probably be only about that tall. All right, so this is out of probably a coal-fired power plant, is what it looks like. So there's different generators that you guys might have seen around your house or whatever. Some of you might have a generator that looks something like this. All right, this is a generator it's a portable generator. If your electricity goes out, you can start this up. It runs on gas. You can plug a few electrical things into here, and 13,000 watts. That's actually pretty big. But you could probably run a good part of your house on this if you had a power outage. A much smaller generator might be able to run like the heat, and maybe like the refrigerator so your food doesn't spoil, and a couple of light bulbs and things around the house. Just some essentials in case you have a power outage. Here's a generator that you might see at school. We have one that's something like this. So if the school loses electricity, all right, the generator kicks on automatically and gives us electricity. And you'll notice if we do lose electricity, you'll see that the amount of lights are minimized. That's because the generator only has a certain amount of capacity, and we use the generator to just provide essential functions in the building. So when there's a power outage, the generator kicks on, and you'll always notice that because the lights will flicker, and then the internet will probably go out, and then there will be less lights that are lit because not all of them are hooked up to the generator. All generators have the same basic parts as a motor: a magnetic field and a coil. In a motor, we saw that we have a stationary magnetic field, and we put a coil in that magnetic field and run a current through it. The generator does the opposite. What happens with the generator is we put a magnetic field into a coil, and the magnetic field pushes the electrons that are in the coil through the circuit, making electricity. So let's look at some basic components or some basic behavior of a generator or a coil in a magnetic field. So what we're going to do is we're going to use a simulation that I wish we could do this on your Chromebooks, because then I could just easily write up a lab and say do this, 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 and this, and answer some questions. However, this doesn't run on your Chromebooks, so I'm going to run it for you on a simulator. Here's our Faraday's law simulator. So this works just like the demonstration that the guy was doing on the last video. So if we move the magnet in, we get some voltage. We move the magnet out, we get some voltage. So the first part of the lab says move the magnet in and out the solenoid and note your observations. So what do? We move it in, we move it out. Okay, so we get voltage. The next thing is place the magnet directly over or alongside the opening in the solenoid and hold it in place for several seconds. So here we go. We're going to set it right by the coil, and what's happening? Place it inside. All right, well, maybe it has to be inside to get electricity. So we'll go and move it inside. Now it's just sitting inside. What's happening? So based on our observations, we would say in order to make current, what has to be happening to the magnet? Just sitting still here, sitting still there. But if I do this, now I'm getting some electricity. So what do we need to do to the magnet to get electricity? Okay, part two. Let's take a look at the galvanometer, or actually this is not a galvanometer. We were using a galvanometer. This is using a voltmeter. All right, so let's take a look at the voltmeter. So I'm going to push the north end into the coil. What do we notice about the voltage? I'm going to pull it from the coil. What do you notice about the voltage? So in, out, in, out. Okay, let's do a similar thing. So in, out, north end in, north end out. Let's flip the magnet. So we flip the magnet. In, out. South end in, south end out. What if I keep flipping the magnet? Well, that's interesting. Never did that one before. All right. So there we go. So we have a case when we put the north end in, we get a certain behavior. Or I should say we put the north end in and out, and we get a certain behavior. And we put the south end in and out, and we get a certain behavior. So let's look at one last thing. Let's look at what happens to the strength of the voltage, or the value of the voltage, based on the speed that the magnetic field changes. So by putting it in and out, we're changing the magnetic field that's in the coil. So there I'll go slow. Whoops, it's kind of hard to do this real nice and steady with my mouse. So slow, out slow, faster, faster, really fast. So we should notice a relationship between the voltage and the magnetic field. So you should be you are in a bad way today. So you should be noticing a relationship between the voltage produced and So you should notice a relationship between the strength of the voltage, the value of the voltage, and the rate that the magnetic field is moving in and out of the coil. So slow, slow. We can also look at the brightness of the bulb, right? Because if the bulb's brighter, there's more power being produced. We learned that last semester. I'm sorry, we learned that last unit, or a couple units ago. So there we go, a little faster and way fast. All right, so there's obviously something there. Okay, we could also do this too. This is kind of cool. So let's switch to just a single coil. Really, really fast. Oh, as fast as I can go with a single coil. Not much is going on. So if I add more coils, boom, I get a whole much better field. All right? Or I should say I get a lot stronger current and higher voltage. So to summarize everything that we just saw, so all generators have the same basic parts as a motor, a magnetic field and a coil. A generator is converting mechanical energy, something is physically making the magnet move back and forth, okay, to produce electrical energy. A generator is basically a motor run backwards. So in a motor, we have a magnetic field and a coil, and we put current into the coil. The current in the coil experiences a force due to the magnetic field because current is moving charges, causes the motor to rotate, so we get mechanical energy from electrical energy. In a generator, it's exactly the opposite. We could actually take an electric motor and spin the motor and hook the motor up to something, and the motor would generate electricity because the magnetic field now is pushing on the electrons in the coil, causing current. So that's why we can always say that a generator is a motor run backwards.